Hello everybody, this is the MATLAB and Simulink Racing Lounge. In today's episode we are going to talk about ADAS systems and how you can develop algorithms on that in MATLAB and Simulink. Well, no worries at all, we will explain what ADAS and active safety systems are. But before moving into the topic, I'm really glad to have Marco on board. Hello Marco.
Hi everybody.
Marco, could you introduce yourself briefly? And then
Y-
we will directly jump into the agenda of today's episode.
yes, I am Marco Rogero. I am a senior application engineer at MathWorks with a focus on image processing and signal processing and ADAS system. And just to explain what ADAS system are. So ADAS means Advanced Driver Assistance Systems. And we have under ADAS all the systems that help us to avoid errors when we are driving and to make our driving experience safer.
Okay, first of all, we will give you an intro to ADAS systems or also active safety systems. Secondly, we are really proud to have a team testimonial. So from the student team, Starkstrom from University of Applied Science in Augsburg have provided us with a cool video. They have been working on the topic for years now. That's a very nice introduction and that tells us this topic is important for you. Then we will move into demos using MATLAB and Simulink, covering certain subjects like lane tracking, adaptive cruise control, also using sensor fusion and radar systems. These demos are accessible for you. We will always provide you with links to our resources, so you definitely can work on them. You can try them at home. And last but not least, you know that we will talk about the key takeaways. We are a bit critical about ourselves. Well, and I think about the trends in automotive industry, you can tell us a bit about the recent stuff, what is going on there, and tell us a bit about the motivation of automotive customers for MathWorks, what they are doing and what they want to do in future.
Yes. So automotive customers for MathWorks, they are working a lot on this active safety system and ADAS system, and we see something in common for all this kind of system. These are systems that have to operate consistently and robustly under unpredictable and dangerous situation, and there is a real need to test and for deep testing of this kind of application. Now, if you want to test all these application on the road, you will have high costs and also dangerous testing that you have to perform. And there is a need to be able to simulate the behavior of the system not only on the road, but with PC-based simulations. And this is actually the main objective that we have that I have today to show you how you can use our tools to develop this kind of PC-based simulations.
And basically, what I can observe, having a look at from the student community, it's pretty much similar. So there's a nice analogy. Having a test day out on track from the student team is huge effort. It's the logistics, it's the cost. So I think that it's very similar for from the student teams. If you can do testing in a simulation environment, that's definitely the side. That's perfect. So there's a nice alignment between Formula Student and the automotive industry.
So let's take as an example of active safety system a lane keeping system in which we have a part of the algorithm which will be focused on image processing and another part that will be focused on the control algorithm. And normally you have two kinds of engineers in the industry, and I also believe in the teams of Formula students that are working on this algorithm. So the first part of the team will probably work with a script language like MATLAB or C, and will take an input from an image and will analyze this image to understand, for example, what are the lanes that that I have in front of me and what is my position on the road. Then this this information, the position on the road, will be used and will be given as an input for the control part of the algorithm. And there you have the possibility with tools like Simulink or Stateflow or other tools in our tool chain to model the control part of the algorithms and also to model the dynamic of your vehicle, so that you can also simulate what the vehicle will do and make a complete PC-based simulation on your PC.
Okay, well, and that's basically a very nice bridge. So you can record a certain video with your car on different circumstances, and then, well, you have that video in place. You can always work on that. You can use it to tune your algorithms. So I think this gives a nice glimpse into the field of simulation-based testing.
Yeah, you can record the video from your cars, but if you want, you can also some other external tools that are based on Simulink to generate, as you see here, we have a picture which is actually not a real picture coming from a real camera, but you can describe the topology of a road and a specific environment, and then you can also simulate with a lot of this third-party software the inputs that you will receive from your sensor, like camera, radars, lidar sensor.
Okay, well, that's pretty interesting. Now let's move on to the example that the guys from Steigstrom Augsburg has provided us. Well, we thought it's best to go with a video. Well, let's start it. And what we see is a skid pad. And if we have a closer look to the top right corner, there's a driver in the car, but the hands are not at the steering wheel. That's pretty interesting. Well, the car seems to be quite dynamic, quite fast. And this is kind of an autonomous system.
Yeah, and it's a complete example. You see, the car will have to recognize these points on the road to recognize the lines that these points are describing, and then use this information to steer. And this is already a very advanced active safety system.
Well, I think now we can directly move into the demos and into the software demonstrations you have prepared for us.
Yes, so we will see some example about lane tracking, so similar examples to the ones that we have discussed so far. Then for adaptive cruise control, we will have a look to tools and possibility that we have to model complete radar systems. And then we will speak about sensor fusion. So how can you use the different informations that you have from different kind of sensor to have more reliable systems that are working even better.
Well, I'm really looking forward to that, especially sensor fusion. I can understand the high-level concept of it. Well, it's not only, I don't have only access to one sensor, but to a set of sensors. But how to get them together and to get a reasonable result out of that, I think that's really interesting.
Yeah, that's really a hot topic also for the industry, but I believe also for the Formula student teams. So here we can see a first example we will see today, Lanekeeping System, like we have seen before in the video. We have a car, we have a camera mounted on the car, and we receive images from this camera. And the first step in this kind of algorithm is normally to make edge detection to identify the object that we have on the road and to identify these lanes that we have. Then we have to identify our position and to calculate our position on the road, and we can generate an alarm signal if we are leaving the lane, or we can organize the system so that our car will steer automatically to keep us on the road.
This is a documentation that is accessible. It's open, it's in the internet. No licenses required. Well, licenses are required to run the models, but you can have a look at that article. You can open that models, you can work with them. You can, well, access the exact demo that Marco will show in a few minutes.
So here I am in the help and documentation of MATLAB and Computer Vision System Toolbox, and here you can see we have for these examples that we have seen before this video, we have a model in Simulink which is doing exactly the same and which is delivering exactly the video output that we have seen before here. So you have already the possibility to use this kind of models as a starting point, and we also have a similar algorithm, or exactly the same algorithm actually, also implemented with in the MATLAB environment, which is doing the same thing. Let's have a look to how does lane detection algorithm look like and what are the typical steps. Here I have imported a picture that I want to use as an input. The picture is composed about two parts. The lower parts with the road, which is relevant and interesting for our application, and the upper part, which is not relevant. So we do not need to process this part of the picture, and we can crop a region of interest and the specific region of the picture, and we will focus on this output. The very first step that we can do is to extract edges. To do that, we can use the edge function. And here you can see the result that we have with edge, and we have used the Sobel version of the edge detection function. We have, as you see here, different algorithms that we can use in this edge detection function. Sobel, Prewitt, Roberts, and Kenny, and others version of the same algorithms. And in MATLAB, you have the possibility to switch quickly between the several versions and to check automatically what is the output that you have. I can change the value of this counter to select the different version. And here you can see, for example, this is the algorithm, the output that we have with the Prewitt algorithm. It's still quite good for our application, still acceptable. Now let's try with Roberts. It's still good. And let's try with LOG. Oh, that's not so good. And also Zero Cross and Kenny are delivering results that are not acceptable. Now, let's go back to Sobel. It is delivering a good result, and we can use it as a starting point. Now, we have this result so far, and we can use some morphological operations to improve the results that we have. And you see now the objects are better defined. And also I see here a very good value of this Formula Student project. This is not only a kind of work which make you fit for the automotive industry, you learn a way to work which will make you fit as an engineer or developer to also solve a lot of other problems. You see now, for example, these objects are quite large, and we can simplify them and extract a small line for each object that we have there. So now we have some lines composed of some points similar, and in the next step we want to change the perspective. So now we are seeing these points from this perspective of a camera, and now we want to use a matrix transformation to make the next steps and to have the same kind of points but visualized as we would be on a helicopter and we would observe our vehicle from the top. This is something that we can easily do with MATLAB. And here you see it. You have the same points, but just from a point of view which is independent from the camera position. And the car is really here in the middle, in the position 0. Now we can select some region of interest on a specific lane and some reference point. First one. And now we want to find the mathematical description of one line which is following all these points that we have on the road. And we will use here these green crosses that we did mark on the display. To do that, we use a curve fitting tool. And here you see these 4 points that we have identified here. We just have to find the mathematical description of one line which approximate in a good way these points. And I know that here a polynomial equation with a of second degree would fit our results. And here you see the result is quite good, and we can proceed and check if this is working also on our application here. And here you see we have one line which is describing really well the direction that we have on the road, and describing really well the position of all these points. Now, this is an algorithm.
Well, quick question here. In that case, you used a quite low order of a polynomial to specify a curve. Not sure whether all chicanes at a Formula Student racetrack can be covered using that, but well, it would be no problem to go for higher order polynomials or even for well, stepwise functions.
Yeah, that's a good point. This is something you have to check. So the second degree, it's okay on not too complex roads, but maybe you will have to select something else in the tools that we have seen before. And now this result and this analysis is something that we have done for one frame. I have another small example here in which we make the same analysis from a video, and let's have a look to it.
We see the cropped camera video, we see the edge detection, and at the end all the way down to dynamic simulation of
yes
detection.
We have the same algorithm we have seen before in the background, and you can see the result. You can also see we are changing the lane that the algorithm will detect two others lanes.
Well, I believe that this is running in MATLAB. This is all working nicely, but at the end it has to run on a car, probably on an ECU or on a microcontroller. How is the workflow to get it running on a proper car?
So the workflow. First of all, you can design your algorithm without thinking about the final implementation. So you define the mathematical concept and the mathematical algorithm, and then you can use the MATLAB code or the Simulink model that you have developed and generate C code, which is also embeddable on your microcontroller and DSPs to have them run.
Okay, well, and this is for you guys watching, closing the loop, because we have already had episodes talking about code generation using the embedded coder. And well, what will happen in that example, or what automotive customers will do in that respect, they will design their system using MATLAB and Simulink, and at the end they will use code generation to well, as you said, Marco, embed it onto the microcontrollers in the car.
Yeah. Now, the second topic that we have is how can you model radar system for adaptive cruise control? So we have tools in our tool chain like Phased Array System Toolbox or RF Toolbox that allows you to make a complete simulation of this kind of system. Now, we will go a little bit less in detail in comparison with the image processing part that we have seen so far, but you have the same possibilities to model this kind of system and to extract the information. And for example, here we can see an example for a FMCW radar. So FMCW stands for frequency modulated continuous wave radar, and you can use it to estimate the distance from a car in front of you or from another object in front of you, and also to estimate the speed of this object. And so here you can see the same script that we have seen in the documentation, in internet, or in the product. You find here the same kind of information, just in the MATLAB editor, with a lot of comments that you can use to understand what is going on. And then you can run this algorithm to create the first variables that you need to create the waveform.
Well, you mentioned the expression waveform. What exactly does that mean? What is that?
Yeah, exactly. That's a good question. So the waveform is the description of the signal that I will send from my radar system. Here you see we have a signal which is varying the frequency with the time, and here you see, for example, the frequency is changing with the time, and we have this ramp that we can use, and this is what we mean if we say waveform of this FNCW radar signal.
When you see that frequency plot over time, what does it tell you? Is there a distance getting bigger, getting smaller, or what do you see when I have a look at this diagram?
So this is just the signal that you will send, and you will receive back another signal which will be different than this first signal that you have sent, and you measure the difference in the frequency, the bit frequency, to analyze the range, so the distance of the target and also the speed of the target. And you have the tools with this phase array system toolbox to simulate all the path and for the signal processing, and at the end to extract a result like this one. This is a classic visualization of radar results. So this range, speed, response pattern. You see on one axis you have the speed of the object that you have detected, and on the other dimension you have the range, so the distance between you and the targets. And here, for example, we see a peak in this point, and we can say that so the speed of the target is 0 or next to 0. So this means that this is probably a car which is moving in front of us with the same speed of our vehicle, and then the target is at a distance of something more than
A little bit more than 40 meters.
and this is the final results that you have there. Here you see we have also a Simulink model running a simulation of FNCW radar system in which we have two targets. You see here the results, so the waveform that we are using, this FMCW waveform. And here you see that with the time we are increasing the precision of the tracking results. And here we can see two targets with these two different positions and speed.
Was a nice example involving Simulink. But could you comment, Marco, on where to use MATLAB and where to use Simulink, just for viewers that are not so much into the topic, to distinguish what tool is the best solution for their application?
So both tools and both environments are really good for that. For this kind of application, you can also do almost the same things in MATLAB and Simulink. In Simulink, it is easier to organize a time-based simulation. In MATLAB, you have to programming something more, but what I see for the users that I am in contact with, it's a matter of taste. So some of them prefer to use MATLAB, some of them prefer to use Simulink. Maybe is MATLAB the most used solution? In Simulink, I think that it is also, if you work in a team, it is much more intuitive to understand what is the structure of the system and what is the system doing. But both tools are good.
Okay. Okay, well, and we have provided you with two links, one using MATLAB, one using Simulink. Have a look at it. Let us know what you prefer, and if you want us to go more into the details, we can do that in via our communication channels, or maybe if it's a very important topic, to do another episode in future. Let's see. I think at that point, thanks very much, Marco. Let's move to the slides again and have a look at our third demo example, which will talk a bit about sensor fusion, but already at that point, pretty impressive, pretty enlightening today.
Now let's speak about sensor fusion. And so we said that we need sensor fusion to have much more reliable systems. And just take an example here. We can speak about, think about a car equipped with an advanced cruise control system, automatic cruise control system. And So let's think to a car which has only one radar system, and this car will detect one or two vehicles depending on the radar system that you have mounted on it. And in this situation, so you see here two vehicles in front of the car. One is the nearest vehicle to the car, and it is also the slower vehicle probably. And so if we have only the information coming from the radar will say, okay, here I have a vehicle in front of me. It is slow. I have to focus to this vehicle to be able to make my decision. So to be able to set my speed, my desired speed. And actually, if we have a look to the picture, we see, okay, we are on a curve. And so this car is on the same lane of this car. And actually, this is the relevant vehicle for me. And this is a situation in which the radar information could be not enough. Then let's think about a situation in which we do not have only the radar, but we also have the camera. Now, here with the camera, we would be able to make a lane detection and to understand, okay, I am moving in this direction. So this is the vehicle which is interesting for me.
Okay, so quick question at that point. So the radar would be able to see both cars, but it would focus on the slower car, which is closer to me, obviously.
It depends on the radars that you will use. So you can have radar system that will be able to detect both cars and also the angle and the position of the cars. But with the camera information, you will be able to have more precise information. This is only one thing that you can do with the camera to understand what is the direction that you are on. And on the other side, you can also use object detection from the camera and have two separate list of objects that you have detected. One is coming from the radar that is saying, hey, two objects in this position with this speed. And one other is coming from the camera, which is saying, hey, I see two objects in more or less this position without information on the speed. Now, all these sensors, they have advantages and disadvantages, and you can take in account these advantages of disadvantages of a sensor system, and merge and fusion the information which are coming from the sensor to have a reliable list of objects with much more reliable information. And this is something what we have implemented here in this demo model. You see the result here. The same situation. Now you see two cars. This is nearest to my car, but I am focusing on this one, and I am able to switch quite quickly and identify the objects that are interesting and relevant for me. So this is an example of sensor fusion. And also here we have a lot of tools with Computer Vision System Toolbox or DSP System Toolbox and the MATLAB and Simulink environment that allows you to quickly test your ideas and find the right solutions.
Marco, let me try to summarize it to see whether I got that. Sensor fusion, in that example, it's pretty convincing, and say I combine a radar and a visual sensor, a camera, to identify the vehicle that is most crucial to me. The vehicle was always marked in red. So is it right to say that sensor fusion, well, is the combination of different sensors, but sensor fusion is not a technique. It's mainly describing a full environment where I'm smartly combining different signals and while combining them in an algorithm that does certain things.
Yeah, normally sensor fusion is an algorithm in which you combine this information that you get from these several sensors. There are several kind of sensor fusion architecture, which advantages and disadvantages, but it's mainly an algorithm in which you use all this information that come for all these different sensors, which we did speak today about radar and cameras, but you can use information coming out from a lot of other sensors.
It was not the objective of today's episode to dive deeply into sensor fusion, but I think it was a very good closing point, well, because it shows a wide field of possible application. Marco, at that point, thanks very much for the demos, and this moves us to the key takeaways.
So, thank you, Christoph. I think I would be really happy if I would be able to deliver today these three messages. One is that with MATLAB and Simulink, you have already the right tools that you can use to model and simulate this kind of systems. Then an advantage that you can have, and this is the second point, is that you do not have to test so much on the road or on the test track, but you can already do a lot of simulations with your PCs and in an easy way without using your car prototype and simulate the most part of the things on a PC in a realistic simulation. And then that you have the possibility to model and to simulate almost all sensors that are used in ADAS system today in the industry or in the sport application.
I think there's nothing more to add from my point of view. Especially the third point, we have seen that clearly. So you don't necessarily need a actual video recording. You can have a video from a simulation environment, and it can give you the same benefits. Well, at the end, we hope that we have enlightened you a bit on that field of application. But as usually for very interesting topics, I guess we have created more questions than we have answered questions. But maybe this was a bit the purpose of that episode. Marco, thank you very much. This was enlightening. This was convincing. Thanks for all these demos, and thanks for all the preparation
Thank
work.
you, Christoph, and thanks for the attention during the video.
Well, the attention comes from you guys watching that video, so we are convinced that this is important for you, and we try to help. And Marco, this brings us to the end of the episode. So let's go to the last slide where all the information that are relevant for you are summarized. So we definitely are looking for your feedback. We are looking forward to that. So either via formulastudent@mathworks.com, our team email address, or in the Facebook group. Another link to all the Racing Lounge episodes is also on that slide. So we have, I think, 40 or 41 videos currently. Also a link to the software offer. And if you do use our software, we would be enlightened if you use our logo onto your car and on your reports. Well, thanks for watching, and hope to see you next time.
Thank you.
Bye-bye.
Bye.